Welcome to this lecture. In the previous lecture, we are discussing about the variational principle, and we will continue our discussion from there. In the last class, we defined what variational principle offers. Just to remind you, variational principle tells us that if we have a problem, if we have a system whose Hamiltonian we know because we know the system, and suppose it has some terms which makes this Hamiltonian too difficult for exact solution of the Schrodinger equation. In that case, what we do is that we can start with a trial wave function phi, because we do not know the exact solution and we are interested in getting the exact solution. So, therefore, in those cases we would actually start from this trial wave function phi, and corresponding to this trial wave function we evaluate the energy integral given in this expression, where this involves evaluating two integrals. One is the energy integral corresponding to the Hamiltonian given of the system, and of course the overlap of the trial function. If my trial function is a normalized function, then I do not have to worry about this term. I simply have to look at this energy integral. By evaluating this, I obtain this E phi. What variational principle tells me is that no matter what is your trial wave function, the energy that you are obtaining is always going to be greater than the ground state energy. What is ground state energy? The ground state energy is given over here. If I had the exact solution of the ground state wave function, then I can of course obtain the ground state energy, but in those cases where exact solution is not possible, of course I do not know psi 0, but therefore I also do not know exact value of E 0. But variational principle offers me this condition that do not worry, no matter what trial function you take, the energy that is coming out of this evaluation of this integral is always going to be an upper bound of this ground state energy of the system. In other words, it also tells me that as my trial wave function would approach the real wave function, the real eigenfunction, that would be reflected in the energy. That means the energy E phi that I am obtaining will also approach the ground state energy. Now, since I do not know the exact value of the ground state energy, how would I ensure that it is actually approaching the ground state energy? That is where variational principle helps us, because it tells us that no matter what trial function you take, your energy is always going to be greater than the ground state energy. So, therefore, you go on minimizing this E phi. That means the energy that you are getting because of this trial function as much as you can, and the lowest possible value of the energy is going to be the best description of the ground state energy. Whether how well it works, we will have to see that when we take a few examples, but before that we would look at the justification of this principle. Now, suppose we have this Hamiltonian we have here. Let us assume that the true eigenfunctions are given as psi i's. In those cases which I do not know, of course, there is no way of knowing this, but in those cases where actually the true solution exists, we can at least pretend that we start from another trial function and then see how variational principle works for those systems where the exact solution is known. We will look at those kind of examples also. So, suppose if we knew the true eigenfunction, suppose if they were psi i's, then I would have obtained this E i's as the corresponding eigenvalues or the corresponding energy levels of this system. Now, the trial wave function that I am taking phi can be expressed in terms of these psi i's. Why? Because these psi i's are eigenfunctions of a Hermitian operator, that is the Hamiltonian. Now, we already know that the eigenfunctions of a Hermitian operator form a complete set of orthonormal basis functions. So, by that I mean that I can express any arbitrary function, in this case the trial function phi, in terms of this complete set of basis function, that is psi i's, with the coefficient Ci, which suggests that what is the overlap or what is the similarity or resemblance of this trial function with an individual eigenfunction. The psi I is one of these many eigenfunctions of this Hermitian operator, that is the Hamiltonian of the system. So, this we already knew from the principles and postulates of quantum mechanics. So, if we can in principle express this trial wave function as a linear combination of these wave eigenfunctions of the Hamiltonian, then we can obtain the expectation value of the Hamiltonian operator as following by evaluating this energy integral. You would see that when I evaluate this energy integral, you would see that if I put this linear combination of psi i's as phi in both bra and ket, I will end up in getting an expression like this. We already had seen this expression when we were discussing the postulate 4 of quantum mechanics. What does this tell? It tells me that the energy expectation value is simply Ci square or Ci square multiplied by Ei. So, Ci square simply represents that what is the probability of observing energy Ei, the ith eigenvalue, what is its probability to be observed is given by Ci square. So, if my system is one of the eigenfunctions of the operator, then I will get only that corresponding eigenvalue with coefficient of that eigenvalue as 1. All other eigenvalues will have 0 probability to be found, because the system exists in one of these eigenfunctions. But if the system does not exist in one of these eigenfunctions, that means we are talking about a trial function phi over here, then I would get a distribution of energy. So, I would get E1 C1 square time, E2 C2 square time, E3 C3 square time, and so on and so forth, where sum of Ci square for all I would become 1. That is the necessary condition, because our wave, the trial function phi is normalized. If we have normalized the trial function, then you would see that Ci mod square sum over all our i's would also would become 1. Now, let us expand this term by taking first few terms. So, the first term in this sum is C0 square E0. So, 0 is the ground state, E0 is the ground state energy, and C0 square is its corresponding coefficient, plus U1 square E1 plus, and so all other higher energy terms would appear here. Now, the line, the first line and the second line, the difference between them is that in this second term, third term, fourth term in the first line, I have E1, E2, E3, all these energies, which are the excited state energy. So, the E0 is the ground state energy, E1 is the first excited state energy, E3 is the second excited state energy, and so on. The second line, what I have done, I have replaced E1 with E0, E2 with E0, and all other excited state energy I have replaced them with E0. When I do that, since I know that all these excited state energies are going to be greater than E0, so therefore, I have used that the upper line, this line, is certainly greater than or equal to the lower line. Now, when you look at this second line over here, you see that each term over here has E0 in it. So, I take them common and then take over a summation of all the Ci's. So, what I would have is that Ci square into E0 as this. Now, what do I mean that? What do I obtain from there? So, from there I would obtain that no matter what is my trial wave function, the corresponding energy, the expectation value is always going to be greater than E0, and it can only be equal to E0 only when this inequality will become equality only under one condition. The condition should be that C1, C2, C3, C4 and so on should become 0. Only C0 should survive, and therefore, C0 value will become 1, and when I multiply 1 with E0, I would actually get E0, and only in those cases I would get this equality. So, in other words, what we see is that since the trial wave function can be expressed in terms of as a linear combination of the exact eigenfunctions of this Hamiltonian, we have this beautiful relation which tells that the expectation value coming from that trial wave function phi is always going to be greater than the ground state energy. It would only become equal to ground state energy only under one condition, when phi, the trial function, is identical to psi 0. Only in that case the E phi will become equal to E 0, otherwise it will always be greater than E 0. So this is the basic idea behind a variational principle. Now the next question is that how do we implement this idea for a system? So what would be our strategy to do variational calculation? The strategy is the following. Since variational principle tells that E phi is always going to be greater than E 0, so it indicates that I can minimize my E phi as much as I can, and the lowest possible value of E phi is the best possible answer to my E 0. Now in that case, what strategy can I use? I can do the following, that when I am using this trial function, when I am defining this trial function, I would define the trial function as a function of a parameter alpha, which can be fitted. So this parameter I would incorporate in the functional form of the function, so that when I change alpha, the wave function can also change. What would be the result of that? When my phi is a function of phi of alpha, I put this idea into this expression E phi. So you would see that when I evaluate this energy integral, I am integrating over all the coordinates of the system that I am considering. So therefore they will all be integrated out. What would still remain is that this E phi will again have a dependence of alpha, because my phi, the wave function, has a dependence on alpha. So after integrating and obtaining the energy integral and the overlap integral, the E phi that I would get would still have a dependence on alpha. Now why is that important? Now we see that E phi has a dependence on alpha, and I want to minimize this E phi as much as I can. How would I do that? I know I can take the first derivative of this E phi with respect to alpha, this is the parameter, and try to make that 0. When I evaluate this equality, that means I would try to find out the value of alpha that minimizes E phi, that gives me the lowest possible value of E phi. That minimum value, I call that as alpha m. Alpha m is the value of alpha which minimizes the energy, and phi of alpha m. So this alpha value which minimizes the energy is the best description of my wave function, given the choice I have made on the trial function. So what is the best form of the trial function? That I would get simply by replacing alpha in the trial wave function with its alpha m, which is the value that minimizes the energy. And what is the best energy? That I would get by replacing E phi of alpha, by replacing alpha with alpha m in this energy expression. So by following this strategy, I get the best possible description of the wave function, best possible description of the energy, given the choice I made with respect to the trial function. So all this explanation works only when my trial function makes sense. If my trial function is by design a bad trial function, no matter what I would do, I wouldn't be anywhere close to the real solution. But for every trial function I make, I can make an estimation as to what would be the best energy that this trial function gives. Now someone else can come and say that no, you change the trial function from this form to another form. Would I know how, whether to believe this or take this advice or not? The way to judge another wave function, another trial function is simple. Again, take that new trial function, do this exercise and see whether that trial function is giving you the energy E phi alpha m, which is lower than your first trial function, and if it gives, that means that trial function is a better trial function than your trial function. This way I can also judge which trial function to take. But no matter what trial function I take, whether that result is reliable or not, that is a different question that we will discuss, but there should be some basic conditions that the trial function should meet. For example, it should satisfy the boundary conditions of the problem. So suppose if you are talking about the particle in a box, so where the height of the barrier is infinite, that means the particle is going to be trapped within the box forever. In that case, I know that the wave function should ideally become 0 at the boundary region. So that boundary condition should be met by this wave, the trial function. And the other condition is that the trial function should also be a well-behaved function. Why so? Because you see, when we have defined a trial function, we also have to evaluate these energy integrals, the overlap integrals. So therefore, this function should be square integrable. So that imposes certain conditions which we call the wave function should be well behaved. So therefore, these two conditions should be satisfied for us to consider a trial function. So this is what the variational principle is. This is what the strategy for the variational calculation is. Now, so far what we have discussed is that the variational principle talks about the ground state energy, that is E0. It says that the vibrational it says that the E phi, the variational energy E phi at alpha m, the best value of E phi is always going to be greater than E0. But what if I want to get the first excited state? What if I want to get the second excited state? Can I use variational principle? The answer is yes, but with some caveats. This is what we are going to discuss next, is the variational principle for excited state. Now, the variational principle statement remains the same. To justify the use of variational principle for excited state, we again take help of the same condition, that let us say that the trial function can be expressed as a linear combination of the psi i's. Psi i's are the true eigenfunction of the Hamiltonian, which Hamiltonian is Hermitian operator. So psi I form a complete set of orthonormal eigenfunctions basis. So therefore, I can express the relation over here, where Ci is simply overlap of psi I with phi. This is what we even discussed in the previous case for the ground state. Now, when I am talking about the excited state variational principle, I impose one more condition. That condition is that the trial wave function, in addition to satisfying the other condition that we discussed, in addition to those conditions, it also must satisfy another additional condition. What is it? That the trial wave function must be orthogonal to the ground state wave function. If I am interested in getting energy using variational principle for the first excited state, this is again a necessary condition, that my trial wave function must be orthogonal to the ground state wave function psi 0. When this condition is met, psi 0 phi overlap is 0, that means C 0, the contribution of 0th eigenfunction to the overall eigenfunction becomes 0. So that's what Ci equals 0 means. And with this condition imposed, if I evaluate the expectation value of the energy, then I would see that this is the expression that I had seen in the previous case also, except for one change, is that in this summation Ci is not equal to 0. Of course, you can keep Ci as 0, but since already I know when I equals 0, C0 is 0. In that case, whether you keep I equals 0 or not keep doesn't matter. So therefore, I am emphasizing the fact that C0 has become 0, because my wave function, trial wave function phi, is by design orthogonal to psi 0. Here I must mention, it is there are several orthogonalization schemes using which we can make sure that a function is orthogonal to another function, that we are not going to discuss over here. But continuing our discussion over here, if I expand this sum over here, I would see that the first term is C1 square E1. second term is C2 square E2 and so on. Now, in the next line what I have done is I have replaced E2, E3, E4 in terms of E1, because that is now the energy of the first excited state. Here E0 is out of picture because I made C0 as 0. The coefficient corresponding to the 0th eigenfunction, that means the ground eigenfunction, has become 0. So, therefore, the expression starts from E1. Now, if you, just like the previous case, if you evaluate this inequality, you would see that the inequality will turn out to be equal only under one condition, and that condition is when C1 square is 1 and C2, C3, C4 and all other values become 0. Only then the expectation value of this trial function will become equal to E1, that is the first excited state energy. All other possible values of C1, C2, C3s will give us an upper bound of energy for the first excited state of this system. So, that means again, just like the variational principle we used for ground state wave function, we can also use it for the first excited state function, but in this case one additional condition has to be met, that is the trial wave function that we are choosing must be orthogonal to the ground state wave function. Only then we can use variational principle for the first excited state. Now, if I am interested in getting the second excited state, what should I do? Again, this condition can be shown to work even for that. This procedure can also be shown to work for that situation, but again one more condition has to be introduced, that the trial wave function must be simultaneously orthogonal to psi 0 as well as psi 1. So, only under that condition I can use variational principle for the second excited state. So, this way I can go on doing for the higher excited states, but it is not always easy, or it is not even always possible to define a trial wave function which is simultaneously orthogonal to so many different functions. So, that poses a severe condition, but in many cases at least the first excited state can be obtained using variational principle, but they have to satisfy certain condition. One thing that quickly can be expressed is, suppose if you remember the eigenfunctions of harmonic oscillators, the ground state eigenfunction is an even function, the first excited state eigenfunction is an odd function. So, now if you remember, the harmonic oscillator eigenfunctions have definite parity, and the parity depends on the value of the quantum number, vibrational quantum number n. In that case, what happens is that if I am interested in getting the first excited states energy variation using variational principle, then my trial wave function, which has to be now orthogonal to the ground state wave function, I can simply take any odd function as the trial function, and that will become orthogonal to psi 0. When I integrate it over from minus infinity to plus infinity, that will give me an odd function. So, it will become 0, the integral will become 0. So, in that case any odd function would work when I am talking about a system whose eigenfunctions have definite parity. But imagine if I do the same for the second excited state of harmonic oscillator problem, this simple principle will not work, because the second excited state is an even function, and then it does not necessarily satisfy the condition that it is simultaneously orthogonal to psi 0 and psi 1. So, therefore, we quickly encountered this problem that we are not able to define a trial function which is simultaneously orthogonal to so many other functions. So, therefore, the application of variational principle, at least the part of variational principle that we have discussed so far, is very limited when it comes to excited states. However, on the other hand, so far as the ground state is concerned, the variational principle is a very efficient method to obtain an estimation of the ground state energy. So, in this lecture we discussed about the variational principles, its justification, and whether its the strategy to apply variational principle to do some variational calculation, as well as the justification or the procedure as if we can use variational principle for excited state energies. We will look at some examples and study variational principles in greater detail in our next class. Thank you for your attention.